Dear students, in the morning lecture we have discussed DC biasing, MOSFET DC biasing. Continue to that, we will see small signal equivalent circuit. See if you are good at BJT part, whatever discussed earlier in class. See, only thing is the parameters are different. There we will use base emitter, correct? Here we will use gate drain source. Right, so in class like we have discussed DC biasing, right? So three type of circuit we have discussed, like a without RS we have discussed, I hope you remember. Then with RS we have discussed. Then following we have discussed like a dual battery based circuits, right? So continue to that, we will see the small signal equivalent circuit. Small signal equivalent circuit is a mathematical modeling of your MOSFET. So first your DC circuit should convert it into the AC equivalent circuit. Then that AC, that is the MOSFET, have to be replaced by your mathematical modeling. So before that we need to see some small signal parameters. So here you can see the graph. It's giving a clear idea about the changes of ID versus your VGS, that is your transconductance. So the changes of ID with respect to VGS is your transconductance, you are aware, right? So now I'm going to write what is the VGS. See, small v, capital VGS, that means it is a total instantaneous, right? The total instantaneous only we will be writing in small v in the subscript. In the subscript you will be writing your capital. Okay, so total instantaneous is equal to DC plus AC. So DC means you will be using a capital parameter and AC means you will be using the small characters. So here you can see this is a DC and this is a AC. So on the DC it is nothing but a VGSQ, that is this point. So this point you can see this is your VG, and above AC is swinging. So AC is swings. So this is the point where the signal should start. So that is this quotient point. That means your DC, your AC is superimposed on the DC. So this is your DC and this is your AC. So now coming to the main equation, ID equal to Kn VGS minus VTN whole square. So this is this equation what you have calculated, right? So that means I can substitute this part here. When you substitute this whole part, so it is coming like a VGS cube plus VGS minus VTN whole square. So I am just rewriting the terms for my simplification. Okay, so I am writing like a plus B whole square formula. So this is your A and this is your B. So if you write A square plus B square plus 2AB, right? So this is your A square, this is your B square and this is your 2AB. So here this all terms are, you can see all are capital. This is capital, this is capital, this is capital. When you see this is capital but it is multiplied with their small signal value. See this one, it is a noise. It's a in terms of a square coefficient, so it is a noise. So you neglect. So this only be a DC value and this is only be a AC value. So I am rewriting this equation in terms of capital IDQ and small ID. So from here only the master equation you are writing. So capital ID is nothing but a Kn VGS minus VTN whole square. This is for DC. And from here I am writing small ID equal to 2 Kn VGS minus VTN into VGS. So here it is very interesting to see the transconductance from this obtained equation here. So what is the transconductance? We know the changes of ID by changes of VGS. So ID by VGS equal to 2 Kn VGS minus VTN. Okay, so this is one formula. You have to be remember this formula for solving the numericals. So next, if you see GM, same only, you know the formula relation ID equal to Kn VGS minus VTN whole square. So if you see, I want to only this one. That means you want to bring this square to this side, it will become square root of ID. So with that substitution, we will be getting 2 square root of Kn IDQ. So this is a two formula you have to remember for GM based on your condition and problem statement you want to prefer. So another thing, the Kn, you know, it's a conduction parameter already covered in the class. So just I am repeating here. So processing parameter divided by 2, you know, K dash n is nothing but a mu into COX. So mu is a permittivity and COX is your thickness of your oxide capacitance. Okay, so W and L is your width and length ratio. Okay, so we will go to the next slide. So this is very important. So see, now we are going to draw like a mathematical modeling for the MOSFET. So very simple, just follow the lecture. So you you can see this is a MOSFET. So gate, drain, source. Before that, you know, this is like a total instantaneous. You will be representing like a small I, capital D. DC will be represented like a capital I, capital D, and AC value will be represented by small I and small d. So gate, drain, source. Okay, I am repeating again: gate, drain, source, and this is your total instantaneous representation. This total instantaneous representation. This is a total instantaneous representation. Now, very simple. So what you want to do is put on line. So put a yes. These are because see, you are studying only common source. You are not studying common gate, common drain. Okay, so we are focusing only on the common source. From common source we can convert to the other configuration also, right? So with that part we are not discussing, but make sure that we are learning only common source. That's why we are taking common source as a basic reference circuit for explaining all our application and our derivation part. Okay, so what is your input part is your gate. So gate. What is your output part is your drain. So now same procedure. So in between gate and source, you know, the MOSFET is giving the higher input impedance because of the structure. You know, oxide is present below your metal. You know, right? See, already we covered. See, you have a metal, you have a oxide, you have a substrate. Okay, here only the channel will be inversion layer will be that here you have a source and here you have a drain. So here you can see oxide. Oxide is your so is a dielectric material. So it is not allowing electron to propagate. Okay, so here the principle only is a field effect transistor. So that's why you are saying it's a voltage control current device. The voltage across your input VGS is controlling your ID, that is output current. So it should be represented by a higher input impedance. That's why it is represented by the open circuit. Okay, so it is represented by the open circuit. Okay, so that is why it is represented by the open circuit. So VGS. Now you know the output current ID. Very simple. You know the transconductance. From there also we can write. So GM equal to changes of your ID current with respect to VGS. So what is a requirement? I want to find what is ID. So ID is nothing but a GM times of VGS. So it is a dependent current source. So here, so make you can put the rhombus shape instead of circle. So in BJT you used circle, right? Here you can use the rhombus shape just to show the difference. Okay, so the current gain dependent source is GM times of Vs. So this is a model without early effect. Okay, if you are not considering early effect, you will be getting like this. Okay, so this is a model. So same model here also it is explained. Here you can see. So this is your, so in between gate and source it is open circuited. So that means you have a higher input impedance. That's why it is given VGS. Then this is your current, this is your ID current, small I, capital D. So you know the transconductance formula. From there we can write GM equal to changes of ID by VGS. From there I can write ID equal to GM times of VGS. It is a dependent current source. Here another thing, you can represent like a rhombus shape instead of circle. In BJT you use just to show the difference. We can put the rhombus shape for the dependent current source. Then this is your input voltage source and this is your output voltage. That's it. So this is a small signal model for the NMOS transistor. So without yearly effect. See, when you see the yearly effect, see what is the yearly effect, first you want to know. I think you studied in the previous semester, right? So, but I'll just give you an idea. So ID versus your VDS, right? See, you might be getting like this response, right? So when you see here, the R naught is flat, that is the resistance between the changes of VDS by ID. Here this is 1 by R naught, because you are plotted for ID versus VDS, so this is 1 by R naught. Here you can see it is infinite, resistance is huge, right? But there will be the changes, that is there will be some short channel effects or some non-linear characteristics will be introduced in the MOSFET. So there may be changes in your ID current with respect to the VDS. So when there is a linear change in your ID current with respect to VDS changes, that is called as your channel length modulation. During this part only the channel modulation is happening. You can see here the resistance of the channel is inversely proportional to the width and length ratio. The reducing the length leads to the decreased resistance and hence the higher current flow. See, when you keep on, initially the channel was something like this. When you increase the voltage here, when you increase the voltage, what happening? The channel length is modulating. Why? Because when you, this is a reverse. See, this is plus, this is nothing but a bucket of electrons, right? So when you are attracting the electrons, it left out the immobility charge carriers, so that will become like a depletion charge carriers, and the length will be like a changing. Initially it will be something like this. Initially it will be something like this. See, initially your part will be something like this, your inversion region. Then when you increase the VDS voltage, because it is attracting the electrons, so it will left out the holes, right? That is immobility. So what happened? It is something changing like this. So in one point what happened? So see, you can see here in one point, see, this is your your drain, and this is your source. So see, you can, there is a length is modulated. So this all part will be occupied by a immobility charge carriers. Immobility charge carriers. This we used to say as the length of the channel length modulation. Okay, I am not explaining in depth, just to say what is a channel length modulation, just giving an intro part. Okay, so the channel is modulated. So what happened when I am keep on increasing this VDS? Okay, so you can see that now there is a disconnect between the source and drain through this channel. So the obviously no, it will be saturated. It will be saturated because of this resistance. Shall be saturated. But what happened in one place, when VDS is keep on increasing, this will break. This will break, and current will be starting to rise. That is called short channel effect. Short channel effect, we used to say, that is it will introduce a noise distortion in your MOSFET amplifier only, but it's an unexpected part that may occur in your MOSFET that you want to understand. Okay, it's one of the short channel effect that will occur in your MOSFET. Okay, it will break due to the higher voltage. See, when you increase the keep on voltage, VDS is greater than your VDS saturation. So what happened? See, you can see here, it was saturation. It was here itself, it is saturated. Then also I'm increasing, it was like a flat. But in that, if you consider the non-linear, it may go like this. So this only they explained you. So see, the channel. So that's clearly the channel length modulation means the saturation drain current will increase. So this only drain current will increase with respect to the drain source voltage. So please understand, it is a non-linear effect. So when the current is producing, there may be R naught resistance, that is 1 by R naught resistance. So that is called channel length modulation, that you have to be included in your model. Okay, that is the important part. See, the formula for if channel length modulation, if you include, the formula will be rewritten as ID equal to Kn VGS minus VTN whole square 1 plus lambda VDS. Okay, so from here it was calculated R naught equal to, you want to differentiate with this ID by VDS. Okay, so if you differentiate, you will be getting R naught equal to 1 by lambda your IDQ. So this is the formula for R naught we will be getting. Okay, so this will be using in the numericals. Okay, so I hope you are clear. Okay, so finally uh, with the model, with the early effect, this model can be redrawn like this. R naught will be added here. That's all. So I hope understand this is a open circuit because of the huge resistance. The drain current is Gm times of VGS. This is a dependent current source, and R naught is the early effect resistance, finite resistance. Okay, so I hope it is clear. Now we will come to the very important part. In the like in morning lecture, I have discussed like a common source configuration without source resistor DC biasing. So, okay, so this part is the same. Only thing is we are going to see the small signal like analysis. Okay, so already explained in class, right? So how to convert this like a given circuit into the small signal model. First, what you want to do, we want to remove the DC and want to short circuit the capacitor. That is a basic. Okay, so then you want to connect the passive elements to the ground. If you draw for this, what you will get? So you have a MOSFET. So first draw the MOSFET. So name the terminal, gate, drain, source. It is an NMOS, so it should come away from the gate. See, now the capacitor is short circuited. Then this RSI. See, when you remove this DC, this R1 R2 will become parallel, right? So R1 parallel to R2. Then this will come to the ground, right? So this will come to the ground. So RD. So here don't have any resistance, just short it. Here you're taking output. So here small signal, so you want to keep. So this is your just encircle MOSFET. So this is your small signal model. So you can see I remove the DC, it's connected to the ground, it's just come parallel. So that is your RG here. So RG is, this is nothing but RG. So RG is nothing but R1 parallel to R2. The output resistance is only RD. Okay, so this is just to say how to draw the small signal model. Okay, now very important. See, we are going to draw the small signal model. So see, I have explained you the how to draw the AC circuit. From here, what I am going to do, I replace this model. This transistor I have changed like a mathematical modeling, right? So I am going to change to the mathematical modeling. If you change, you will be getting like this, right? You will be getting like this. So what you will put, you will be having your common line. What is a common line? That is your source, and input is your gate, and output is your drain. So I will just explain here. So like when first we will put a mathematical modeling for this MOSFET. So what you will have? You have a VGS. Then you have a current source. You have a dependent current source, right? You have a dependent current source. I explained you in the previous slide. Then they have considered R naught. Okay, that is a yearly effect resistance. So the mathematical modeling is over. Now when you remove this DC, this R1 R2 will come parallel. So I made this R1 parallel to R2. Then this capacitance will become short circuit. Then this RSI will come, capacitance short circuited. Then you have a voltage source VI, input voltage. Then finally this RD will come, right? So RD will connect to the ground. RD. Then finally you have a output V0. So this is a model what they have drawn here. Okay, I hope it is clear for you. Okay, so I hope this is clear. Okay, so the coupling capacitors, actually we have here consider the coupling capacitor, right? So for the coupling capacitor, it is act as a short circuit. The coupling capacitor work only in the lower frequency, right? So like we studied in BJT clearly, like we have studied the response like this, right? So in the lower frequency, gain is limited because of the external capacitor, like a bypass capacitor, coupling capacitor. In the higher frequency, gain is limited, that is a roll-off function is introduced because of your internal mathematical capacitance. So same here also. Only the parameters are going to be different, that we are going to discuss now. See, now what we are discussing is the small signal equivalent circuit of your input coupling capacitor, and we are going to derive the small signal gain. Okay, see, finally what you are going to derive, that is small signal voltage gain for a common source amplifier without RS resistor. That is our objective for this part. So now V naught equal to GM VGS R naught parallel to RT. Obviously right. See, I will put the model. See, you try to put more time. Okay, so then only will be practice VGS. Then here you will be having your MOSFET, dependent current source, GM VGS. Then here you have a R naught, right? R naught. Then here you have a RT. So this is a part I required, right? So this is a ID current and this is your load current. So now what is a V naught they are asking? So V naught is nothing but a I into R. What is the R? So when you are finding R, you want to short circuit the input terminal. So VGS will become 0. So that means this also will become 0. So the output resistance is R naught parallel to RD. So clear now? See, when you are finding the output resistance, you want to consider input is short circuited. So that means this VGS will become 0 and this term also will become 0. So finally the R0 will be parallel to RD. With that, this resistance is calculated. I hope it's clear. Then what is the current output current? The ID is nothing but your GM times of VGS. So ID is nothing but a GM times of VGS. So this is nothing but a GM times of VGS. Why this minus is coming? This minus is coming because your load current, this is your load current. So this is your load current and this is your conventional current. Both are opposite. So in order to introduce this one in the equation, you have a minus. Okay, so minus. So this is your ID and this is your R output resistance. So finally the output resistance is nothing but a small R naught parallel to capital RD, and this is your GM VGS. So I hope it is clear. Now we want to find what is your VGS. Okay, so it is very simple. See here, how we will find a VGS? So go to the previous circuit. So very simple. See, so here I want to find a VGS, right? Here I want to find a VGS. So you can say with me, what is a VGS? Your input voltage source into corresponding resistance. The corresponding resistance is Ri. Ri divided by Ri plus what is the sum of the total resistance in the loop? Rsi. So with that, this Vg was derived, and you can see here this only it was derived. Okay, so I hope this two formula is clear. Finally you want to find what is the V naught by Va, that is a ratio. See, you have a V naught, so substitute this Vgs here. So what you will have? Minus GM. If you substitute this part, we will be having Ri plus RSI. Same you have done in your BJT also. Only thing is you want to correlate and study. So this is your V naught. So you want to divide this by VI, so that you will get your voltage gain A subscript V. So VI will get cancelled. You will get this answer. That's all. So you will be getting minus GM R naught parallel to RD into Ri divided by Ri plus RSI. Clear? Okay, this is for without source resistor. Okay. Now with source resistor. Okay, this is a common source configuration. With the source resistor we are going to discuss. Okay, so you can see in the previous problem, you don't circuit, you don't have RS. Here you have RS. Okay, that is a change in this circuit. So this is a with the source resistor. Okay, so when you draw with the source resistor, you have this RS element, right? So I will explain you very simple. So first what you want to draw is, first draw the center part. Okay, first draw the center part, then you draw the gate, then you draw the drain. So this is your source. So in below source you can see you have a RS resistance, so that have to be included. Okay, then here you can see it was open circuited, right? So here it will be a VGS. So here the ID current will be GM times of VGS. So here it should be short circuited. Okay, so this is your mathematical modeling. So you can see now. So I am repeating again. So in the source you have a source resistor, and in between gate and source you have a drop VGS, that is the input voltage. Then the output current is GM times of VGS. Okay, so other than that you have a remove this supply, so then R1 R2 will become parallel, R1 R2 will become parallel. Then remove this supply, this RD will come to the ground, then V0 I would return, then capacitor will become short circuited and VA you are getting here. So this is your final thing you are getting. Okay, so similarly now when you go for the equation part, okay, so now you want to find your voltage gain formula, that is RD by RS. So how? So same, V0 equal to I into R. Okay, when you short circuit this VI, so your VGS will become 0, so this also will become 0, so this also will become 0, so output resistance only RD. So what is the current source? The current source will be ID equal to GM times of VGS. So with that, V0 equal to your ID equal to GM VGS and resistance is RD. So this equation will be clear for you, right? Okay, now we will find a VI. Okay, so to find what is your voltage gain. So very simple, you want to apply the KVL across this loop in the clockwise direction. Okay, so apply the KVL across this loop. Okay, so this loop. So what you will get? Plus VI, entering at a plus, leaving at a minus. So minus VGS, entering at a plus, leaving at a minus. So minus, what is the ID current which is coming? ID is GM times of VGS. What is the resistance? RS equal to 0. So please remember this is your ID. So ID current is GM times of VGS. So take this to the right side. If you take to the right side, you will be getting plus VGS plus GM VGS RS. So bring the VGS outside, you will be getting VGS into 1 plus GM RS. Okay, now you divide this like a V0 by VA. Okay, so V0 you have a GM VGS RD, VA is nothing but a VGS divided by 1 plus GM RS. So if you divide, VGS will get cancelled and you will be getting this equation. Then what is the equation you are getting? Minus GM RD divided by 1 plus GM RS after removing VGS. See, now I am bringing another assumption where GM RS is greater than 1. Obviously it's going to be greater than 1, so that I remove this one. So GM will get cancelled. So finally your voltage gain is approximately capital RD divided by capital RS. So this is a formula for with the source resistor. Okay, I hope you understand. So this is an exact equation, this is an approximate equation. Okay, now like this is a third circuit, the common source circuit with the source bypass capacitor. With the source bypass capacitor. Okay, source bypass capacitor means you can see it was connected in the source side, so the unwanted noise that will be back to the ground. Okay, so if noise are connected to the ground, it will try to increase the gain. So please understand, if you not connect the capacitor, your gain will be very less. Okay, gain will be very less. If you connect the capacitor here, gain will be more good. So you can try in lab. Okay, so if you connect the capacitor like 100 microfarad or something, here the noise will be bypassed and gain will be enriched to more. If this is not connected, stability may be good, but your gain will be very less. Okay, so this is nothing but a current source. Okay, this is nothing but a current source. It is equal to a resistance. Okay, so it is like a advanced way of representing your like a current source. Okay, so this is a like a constant current source based representation. Okay, so in the latest technology we will be representing like this only. Instead of passive elements, we will be representing directly your current source. Okay, that is not important. Just see, you have a like a bypass capacitor. Okay, you have only the bypass capacitor. So when you connect, okay, so okay, how that model is going to change. Okay, then what is the equivalent circuit that we are going to discuss now. Okay, so for this model, for this circuit, this is your like a equivalent model, right? This is your equivalent model. So like a same procedure, gate, drain, source. So you can put your terminal, gate, drain, source. So see, when you connect the bypass capacitor in the higher frequency analysis, it will be short circuited and this will become negligible in the AC analysis. So this part need not to be considered. You want to put a same like a small signal model. Okay. So see, gate, drain, source, and you have a open circuited VGS. Then this RG I am bringing here. This RG I am bringing here. Then this is a current source, GMVC, dependent current source. Then this I am removing this VD, and this will be connected to ground. So it will be connected to ground, and finally you are getting this model, right? So here finally the thing is this is a small signal model for this circuit. So here we want to find a V0. V0 is nothing but a ID into RD. So you know, same procedure, you want to short circuit the input loop to find your output resistance. So if you short circuit, VGS will become 0 and this also will become 0, so that RD is your output resistance. So input current, your output current is nothing but GM times of VGS into RD. So with that, this output voltage you obtain. So here see, you can see obviously VGS is equal to VA. It is just parallel. So I can write in this situation VGS is equal to VA, because you don't have something RSI, right? See, in the previous circuit you have RSI, right? Here you have some RSI. So you will be finding like a voltage divider rule and you will be finding. But here the case is not like that. You have only RG, so just parallel. So I can put like a VA equal to VGS. With that consideration, I have determined minus GM times of RD. So this is for bypass capacitor. Okay, finally the last circuit is your common circuit with your source load capacitor. Okay, with source load capacitor. So this is going to be already you discussed with the input, and this with your output capacitor. Okay, this is going to be a short circuit, already you know. Just we will draw the model. So very simple. Okay, so first what you want to do is, first you can put your common terminal, that is your source, and input terminal is a gate and output terminal is your drain. Okay, so first you have a mathematical modeling VGS. So here below the source you have a resistance, so that have to be represented RS. So here you have a mathematical dependent current source, GM times of VGS. That's all. Then this is a part R0 I am not including, early effect not including. So here, so this part is over, this part is completed. Now see, I am adding this RG. So I am adding this RG. Okay, then I am considering this VA. Then this I am removing this DC, so it will come ground, RD. So this capacitor will become short circuit. So finally you have a load RL. Right? So that's all. So here you have a V0. So this is a mathematical modeling. This is a mathematical modeling for the output coupling capacitor. Now what we want to derive is, we want to derive your gain, and we want to derive your frequency also we can derive now. Okay, so we know that the formula for finding your cutoff frequency, right? See, this is a capacitor will work in the lower frequency. The cutoff frequency formula is FL equal to 1 divided by 2 pi tau s. What is the tau s here? Tau s is going to be a product of R into C. Here what is your load resistor? RD is parallel to RL. Okay, here you can see the output resistance RD is parallel to RL. So the tau will be RD parallel to RL into your resistance. That is what is the capacitance you have? That is CC. You are finding for this part only, no? So you just multiply with the CC. So your formula will be, cutoff frequency formula will be 1 divided by 2 pi RD parallel to RL into CC. So this is the formula for lower cutoff frequency. Okay, so we can put your voltage gain, we can put your gain also, right? So like when you calculate the VA, what you will get when you apply the just apply the cable in this loop. Already I explained you. So VI VGS plus GM VGS into RS. So this part alone I will draw here. Okay, so you will be confused. Okay, so here this part VGS. So here you have a current source GM VGS, and below you have a RS. Okay, so here you have a VA. Okay, when you apply the KVL in this loop, so what you get? You have a minus to plus, plus to minus, and plus to minus. This current source here is IDGM. So what you get? So VI VGS plus GM VGS RS. So from here you take a VGS common. So what you will get? 1 plus GM RS. So what is the V naught? Because we want to find your gain. So you know that is I into R. So when you short circuit, you have a resistance RD, right? You have RD, and you have another resistance RL. So this will be parallel. So you know that this will be ID into load overall resistance, output resistance. So ID is nothing but a minus GMVGS, that you know is your ID, right? Your output resistance is, you want to short circuit this loop, so this will become 0 and this will become 0, so that this RD will be parallel to RL. So that is your output resistance that you have calculated. That's it. So V naught VI calculated. So now just you want to find it. So V naught by VA you want to find. So from here we can find a VGS, right? So already we know that 1 plus GMRS. So from here I can write VGS equal to VA divided by 1 plus GM times of RS. Why means I want to substitute here, that's why I am doing, so that you will get your gain. So minus GM, so VA divided by 1 plus GM RS into RD parallel to RL. So now just divide with your VA. So VA will get cancelled. So your final voltage gain formula will be, so GM divided by 1 plus GM RS into RD parallel to RL. So this is the formula for the load capacitors. So in the next class we will be starting the higher frequency equivalent circuit.